Syzygy, episode 11, Black Hole Eats Star, then Burps. And welcome back for another episode of Syzygy. This time, we're going to be talking about black holes, which, I mean, let's face it, if you're going to be talking about anything in the universe that's really interesting and kind of cool and a little bit weird, black holes is the thing that you need to be talking about. Joining me at the microphone, Joining me at the what? Joining me at the microphone, as ever, Emily Brunsden. Hi, Emily.
Hello, hello.
So, black holes. We've had a bit of news over the last week or so. Interesting observation in a galaxy some way away. A very large black hole has been eating a star and then burping violently. What's going on?
Well, this is really, really exciting. If the black holes on their own weren't exciting enough.
Yeah, I mean, let's just say black holes, that'll do.
Yeah,
there's a topic right there.
The fact that they exist is amazing.
Yeah, and we'll get to that in a minute because black holes are really interesting in astronomy around the notion of, but what are we talking about here? Anyway, we'll come back to that in a minute. This black hole, assuming it exists, has done something. What's it done?
It has consumed a star.
Right. It's gobbled it up and it's spat some of it back out.
Yeah, into this really interesting energetic jet that we can see.
Right.
So this is a really nice paper by S. Matilja and et al., and they're from the Tirolo Observatory in Finland. And what they have done is over quite a long period of time, more than a decade, they've been looking at this supermassive black hole, which is in the center of a galaxy. And they have observed this flash of energy come from it. They first saw it in the infrared part of the spectrum, and then later on when they were able to follow that up with radio observations, they saw this jet and the trail ends of what's happened after this star has been all gobbled up by this black hole.
Now, to be clear, I mean, energetic emissions from very large black holes and objects like that, that's not completely rare. It's not the fact that we've seen a black hole emitting jets of energy is the really exciting thing here, because that's actually reasonably common, right? Black holes grow by gas and dust and nearby stuff gravitationally being attracted around it or orbiting around it. It's not quite the image that you sometimes see in the media of basically stuff going down a plug hole. A black hole is just a gravitational object like any other, but material can fall into the black hole, and when it does that, there can be very large amounts of energy both taken into the black hole but also swirling around and emitted as these jets. So that's, we see that sort of thing.
Yeah. Well, this is the very first time that we've seen it in process, if you like.
Right.
It's the first time we've been able to image the formation of the jet that was produced when the star fell in. And it's the first time we've been able to measure the expansion of this jet following the gobbling up, if you like, event.
Right. So what's happened here? We've got a star which is getting a bit too close to this supermassive black hole, and it's being torn apart because it's not like a snooker ball on a snooker table just falling into a hole. This is a star which is being influenced by an incredibly strong gravitational field, and it's literally being ripped apart.
Yeah, so stars are basically giant balls of plasma, which acts a little bit like a gas in this scenario, and where the gas or the plasma was stripped off of this star as it came too close to the black hole. About half of that material fell into the black hole. It's gone. We don't see it or any sign of its existence. And about half of that material was flung up perpendicular to where that star was going, orbiting around the black hole, and flung out in this enormously long plume that we call a jet.
Now, why? Okay, there's so many things here, so many things. So we need to create a bit of a mental list here. There's a bunch of things that are coming up in my mind. Number one is, okay, black holes at all. We need to talk about those. What are they? How do we know? Etc. Supermassive black holes in the middles of galaxies. Interesting. We need to talk about that. And then something you just said there, which was that the jets are being shot out in a direction which is perpendicular to the way the star was going around the black hole in the first place. So why?
Wow. Okay.
Why? So let's start. Let's wind it right back. That's what's going on. Star being torn apart by supermassive black hole in a galaxy far, far away. Great. Good start. Well done. Let's talk about black holes. What's a black hole?
Okay, well, a black hole started out as a really theoretical, mathematical concept. And I think one of the nice ways that I can think about a black hole is that, let's start with the Earth. Right, we've got the Earth, which has mass. It's got something like 6 times 10 to the 24 kilograms of mass, right?
Big number, yep.
Big number, so it's quite massive. And we stand on the surface and we're stuck to the surface by gravity, right? Now, if we want to leave Earth, we have to go at a particular speed, which is called the escape speed. And for the Earth, that speed is something like 11 kilometers per second. So if you want to send a rocket up into space, if you don't want it to fall back down to Earth, you must be travelling at least 11 kilometres every second.
Right, which is why rocketry is so hard,
Yeah.
right? If you want to actually get something out there, you've got to work really hard to do it. You can't just sort of drift upwards. You've got to put a controlled explosion underneath you to push you up really, really hard to get you going incredibly fast, just to make it away from the Earth's gravitational field
Yep.
to be able to get out into space.
Yeah, so big rockets.
Yeah.
Now, if we go to something more that has more mass, then you're going to have to go faster.
Right.
So the sun, for example, if the sun is something like 2 times 10 to the 30 kilograms.
So that's like 1,000,000 times more
Yes.
than the
yeah.
Earth.
Yeah. Now, if you want to escape off the surface of the sun, which you shouldn't be there in the first place,
But if you are there, you might want to escape. So
you
I
are
can see why.
then you have to go at about 618 kilometres every second.
That's fast.
That's really fast. So the more mass that the object has, the faster you have to go to get away from it.
Right, makes sense.
Yeah, okay. So now let's go to the limits. What's the fastest thing that you know?
Well, that's easy. The speed of light, right?
Speed of light.
That's the cosmic speed limit, approximately 3 times 10 to the 8 meters per second.
Right.
Right.
So what if
So
you...
300 million meters every second, that's as fast as you can go.
That's as fast as anything can go. Nothing can break that.
Yep.
So what if you're on an object that the escape speed is faster than the speed of light?
Okay, so mental sort of thought experiment here. What if you had an object that was so big that its gravity was so strong that in order to escape, you had to go faster than the fastest thing?
Yes.
Okay.
Yeah.
Obviously, there's a problem there.
Yeah, you can't do it.
So this is the theoretical construct that you were talking about. Like,
Yeah.
let's imagine what that would be.
Mm-hmm.
And that's a black hole.
Yeah. So light can't escape from it, which means that the normal way that we look at the universe is we wait for the light from all these objects to come to us. Black holes are not putting out any of that light from their surfaces.
For the very reason that light can't get away from their surfaces, as we just discussed. That's by definition. Okay. But I mean, I can imagine all sorts of things that are impossible. So, as a theoretical construct, fine, except that if you do the maths, if you go and figure out, all right, so how big would this thing actually have to be? How heavy would it actually have to be? How much mass? Mm-hmm. You need to be careful about these terms because heaviness, anyway. How much mass would it have to have and how big would it have to have this faster than light escape velocity? And it turns out that's possible. You could do that. You could make one of these things. Okay, not on Earth. You wouldn't want to do that. But it's possible. And in fact, it's possible when some stars reach the end of their lives. This could happen.
Yeah, and it's the density that starts to matter too, because it depends on how far away you are from the surface. So the traditional way that we would form a black hole, let's say we want to go and make a recipe for a black hole.
Let's be traditional
Very
about our
traditional
black hole.
Yeah.
None of these newfangled black holes.
Is that when very, very large stars come to the end of their lives, they're left with this core of material, which is all the ashes from all the nuclear fusion that's gone on. And that core is now trying to support a huge star. So a star is basically trying to collapse itself under its own gravity because it's got so much mass, or any object is. The problem with the stars trying to collapse themselves under their own gravity is you've got to have something holding them up.
Right. I mean, otherwise it just collapses down further. But I think everyone can probably visualize that if you squeeze something down, it might give to a certain degree, and then eventually the stuff itself starts pushing back. That you can only squeeze material, stuff, matter, atoms, together so much before they start bumping into each other and pushing back. I mean, that's what you feel when you push on something.
Yeah.
It pushes back. So gravity's trying to draw the stuff of the star together down towards the center, and the stuff is pushing back.
Yep.
Okay.
So you can start off by thinking of the parts of atoms. So you've got electrons and protons that are pushing back. Eventually, if you keep squeezing, putting more mass on, having more gravity, squeeze, you actually squeeze together those electrons and those protons, and you create neutrons. So the very highest density normal objects that we have in the universe are called neutron stars.
And these are amazing things. There's always some statistic that gets thrown around that a teaspoon of matter from a neutron star weighs as much as the Earth or something. Like something insane like that.
So they're about the mass of the sun, but compressed into something the size of about a city.
Okay, okay, seriously heavy. And this is, as you say, this is where you've got so much mass and there's just not enough outward push to be able to control that contraction, to the point where even the atoms themselves have collapsed down and just made just neutrons, just nuclear stuff. It's like one big seething nucleus of stuff the size of a city, which already blows my mind. But here we are. Okay, carry on.
And so those neutrons can squish together pretty tightly, obviously, to get so small, but they can't hold up an infinite amount of mass, right?
Well, I mean, it doesn't even have to be infinite, does it?
No, they can't hold up, anything that's too heavy. So if they're trying to hold up, I think it's about 2 to 3 times the mass of the sun or more, they just can't do it. And this pressure that the neutrons create, which is called neutron degeneracy pressure, fails. So they can no longer hold up all the mass of the star, and the whole thing just collapses, boom, down, and now you've created this theoretical construct of a black hole.
Right. So the neutron star, it's at its last defense. We're just holding up, and then, no, we can't do it anymore. And even that collapses down. So we now have an object which is dense enough, because as you say, I mean, it's not just the mass, it's the density, that the closer packed things are, and the smaller a massive object is, the greater is the force of gravity at its surface, right? So you can have something which is the mass of the sun and really, really big, or you can have something that is the mass of the sun and really, really small, and the gravity will be incredibly intense for the small one. And at that point, you've got this theoretical idea, which is, well, now we've reached the point where not even light can escape. So what is it? I mean, if you were talking about, you've got a neutron star, blows your mind, but at least we can imagine it's kind of like, just a bit like one really, really big atomic nucleus of stuff, incredibly dense, ridiculous level of dense. But if that's not it, if it's gone past that point, what is it? What is this thing anymore?
Well, we've kind of broken physics now.
Right. Well done. Well done, everyone. We've broken physics.
So we don't really know exactly what it is. We know that it's got a mass, and that can be a fairly kind of ordinary type amount of mass for something in the universe. So we can have a black hole that's got a mass of, say, a couple of times the mass of the sun.
Yeah, which is not crazy, because
the
sun's actually a moderately small star, isn't it? It's not, it's big for us, hell of a lot bigger than we are, but on the scale of stars, there are stars which are much bigger than the sun.
Yeah.
Like ridiculously bigger than the sun. So to have a black hole, you could make a black hole with something of the order of the mass of the sun. That's not crazy.
No.
We're not talking,
and it's a well-defined mass, and we know we can measure that number. We can see what the space that black hole takes up as. We call it Schwarzschild radius. And what that means is basically that's the distance away from that piece of mass that light can't escape from.
Right. Okay. So you've got this defined boundary around a mass of a particular size that says this is how far away you're able to get before light can't actually escape. Looking at that from the other angle is that's basically the size of the black hole, isn't it? Because anything inside that, whatever it is, whatever's in there, ain't going to get out.
Yeah, and we have no idea what's going on. No idea.
And this is fascinating, isn't it? Because, the concept of a black hole has been around for a number of decades now, right? But it grew out of something very, very hypothetical, very theoretical, which is, well, what if? what if you had this object? Well, let's go and calculate that then. How much mass would you need? Actually, it turns out that's really doable. Okay, well, how big would it have to be? Under what conditions could you make one? Well, turns out that's possible. Actually, these things are probably all over the place. Like, not everywhere. There isn't one sort of on the other side of the moon or anything like that. But they shouldn't be really rare.
No, and we started finding we can't see them directly because they're not having any light put out, but we started finding stars and other objects that were behaving in a way that they were, in most cases, orbiting around something which had too much mass and to not be putting out any light, basically.
Right. There's some fabulous animations out there. I mean, they're animations, they're visualizations of what's happening in the center of the Milky Way galaxy. Work being done by, I think, Professor Andrea Getz, anyway, who's measured the motions of stars right at the heart of the Milky Way galaxy, like individual stars over the course of a decade or more. And you can see these things whipping around something. You can pinpoint it. There's something there. And we know it's there because we can see these dozens of stars being flung around at extraordinary high speeds. And there's nothing there. Or rather, there has to be something there. And it's got to be huge, like really, really massive. But it's invisible. And it's got to be a black hole. Not just a black hole, a supermassive, like really, really heavy black hole.
So that's the kind of the transition. So we talk about these black holes that are formed by stars. We're not very good at naming things in astronomy. These are called stellar mass black holes.
Well, okay, at least that works.
Yeah.
It's better than, QZ943b.
Well, probably our closest one is called Cygnus X1. But
well, okay.
Anyway, so they're a couple of times the mass of the sun, maybe. Now, then you talk about supermassive black holes. And again, the astronomers were not having a very creative day when they named these guys.
Hang on, these ones are really, really big. What should we call them? Oh, I don't know. Massive, supermassive. That'll do.
Yep. So SMBHs, as they're affectionately called in the field, these are 1 million to 1 billion times the mass of the sun.
Right. And they could only, am I right in thinking they could only have got that big through growing? In other words, it wouldn't have necessarily been a huge star that then collapsed down to form a huge black hole, but rather that they've been gobbling up stuff over time.
Yeah, we don't really know exactly how they form, which is quite exciting in itself.
But they're just there.
Maybe they formed from originally a giant lump of stuff that was at the center of these galaxies that kind of came together too fast and therefore collapsed. Or they were built up by lots of these smaller black holes. We definitely don't have stars that are millions to billions times the mass of the sun that can collapse down.
Isn't it cool that we have this evidence, right? Just like as I was saying before, you can see at the center of our galaxy stars whipping around really, really quickly around some incredibly heavy, massive thing in the center of our galaxy. Can't see it. We don't know exactly what it is, but the only thing that it could be from the calculations is a supermassive black hole. That's the only option that we've got. We see evidence for supermassive black holes in the centers of other galaxies as well. I mean, I'm assuming we can't see individual stars whipping around in these other galaxies. That's a bit too much to ask. So what's the evidence?
Well, we can measure the rotations of galaxies, and then we can add up the mass that they must have. I think we talked about a little bit of this when we talked about dark matter, but that also helps us understand the mass towards the center of these galaxies. So we can see them in ordinary galaxies, spirals like our own, or at least the effects that they have on the rest of the galaxy.
So you're saying that if you look at a distant galaxy and you can see how quickly it's spinning around and the distribution of matter within that galaxy, you can sort of work backwards and go, well, in the middle of that, the density of mass is so big, there's got to be something there that can only be explained by supermassive black hole.
Yeah.
Is that the idea?
Yeah. And there are lots of types of galaxies which have very, very special supermassive black holes in their centers. And these are called active galaxies or active galactic nuclei, AGN. Mm-hmm. And these are special types of supermassive black holes that are throwing out huge amounts of energy that we can see. Usually the most energetic form is in X-rays. We can see these big jets coming out from the centers of galaxies in X-rays.
And X-rays, because X-rays are very high energy, right? If you look at the energy spectrum of electromagnetic radiation, right, you've got visible light that we're all very familiar with. That's the stuff that we can see, but it's exactly the same stuff as X-rays and radio waves and what are some of the other microwaves, microwaves and things like that. It's all the same stuff. It's just depending on frequency. And X-rays are up at the very high energy, very short wavelength, very high frequency end of all of that. And so if you're seeing something which is spitting out a lot of X-rays, you know it's very energetic.
And interestingly enough, there's lots of radio waves as well. And the processes that cause radio waves are often linked to the very high energy processes.
Because radio waves down the other end of the spectrum.
Radio waves are actually really low energy, but they come from processes that can only happen when there's high energy events around. So we see these objects in X-rays, and radio waves, and actually in infrared and optical, we can see some of the emissions as well. So they're really cool stuff. They're basically, if you imagine the morphology of them, you've got usually a big disk of material around these active galaxies, and that disk is actively falling into the galaxy, and it causes these big jets because one of two things. If you're an atom heading into a center of a black hole, there's one of two things that can happen to you. You can either fall in or you can get flung out. The only way you can get flung out is along these poles of the disk. So if you imagine you're in a big spinning disk going around this black hole, the other way you can get out is by going along the poles which are perpendicular to that disk. I'm doing lots of hand motions here at the moment, and then I just realised that that's completely useless.
Podcasts are an audio medium, not a visual one. But anyway.
I hope you can imagine that. So you get these enormous jets of material. They can travel at fractions of the speed of light, which is very, very fast, and they're very high energy. They can crash into whatever medium is around them in the galaxy, causing lots of really interesting effects. So they're really exciting places.
And really noticeable as well. Like if you see one of these things, something is going on there. And again, working backwards, you can go, well, that's really a lot of energy being thrown out in these jets. There's got to be something extraordinary happening in the middle there.
Yeah.
Involving something probably very, very heavy.
Yeah, and they're called sort of feeding black holes, basically. And we see them at all sorts of different angles. We can see the disks in some cases, or we can see them edge on, so the disk is hiding. And we can see the jets on some angles, and then sometimes the jets are pointed towards us. It's all very exciting. So now that probably, we didn't really think that that type of supermassive black hole was in the center of this galaxy that we're talking about. It doesn't actually have a jet most of the time.
Right, going back to this news story.
Yeah.
Yes.
So this galaxy is actually, it was called ARP or ARP 299. Lovely catalogue number again. It's another type of really exciting object. It's a set of colliding galaxies. So galaxy collisions are actually pretty common in the universe. Galaxies are not very far away from each other, generally. So this is an example of two of those galaxies coming together, which makes it a really interesting system in its own right. I mean, you've got bits of gas being pushed and squeezed together. You've got stars being formed out of this gas that's now being thrown around the place.
The thing I love about galaxy collisions is it you know, we're so used to the concept of a collision on our time and energy scales. You know, two cars smashing together, bang, there it is. That doesn't happen with galaxies. It's over enormous periods of time. And actually, I mean, isn't it true that statistically, when two galaxies collide, no individual stars will actually come together? You know, they're so spread out.
Yeah.
But if you look at the effects of the gravity of the two bodies, the two galaxies coming together, it's actually an incredibly energetic event, just really spread out over timescales that blow our minds.
Yeah, it changes both the galaxies forever, and it changes the way they make stars and the way that what types of stars they make. It's so exciting. I mean,
we've got a whole other
it sounds like a real
slow-mo
kind of thing that's not actually going to be very interesting, but really colliding galaxies are lots of fun. So these ones are nearly 150 million light years away, which means that they're quite close.
Okay, yeah, again, it's that scale thing, but yes, that's close on cosmic scales.
Yep. And we knew that there was a supermassive black hole in the center of one of them, and it's about 20 million solar masses. So,
Okay,
sort
sure.
of fairly typical center of the galaxy kind of thing.
Yeah,
And
it's
it
a
wasn't
moderately massive black
And
hole.
it wasn't doing anything particularly energetic or particularly exciting. It was just sort of chilling out, being its black hole self. Yeah. Now, what we think has happened is that a star, which was maybe a bit bigger than twice the mass of the sun, has come a bit too close to this black hole, and it's been ripped apart. As we mentioned before, about half of its material vanished into the black hole, and half of it formed this brand new jet, which was perpendicular to the disk. And it is this jet, and the flash originally occurred in the infrared part of the spectrum, and we found this flash all the way back in 2005.
Years ago. Yeah. Ancient history.
Yeah. Well, in fact, they weren't even looking for a star. It's one of these wonderful things. We weren't looking for that. We were looking for supernova in this galaxy, and because they're colliding galaxies, there's lots of supernova going off. So looking for supernova in the infrared, found this big flash, thought it was a supernova for 6 years or so. Then turned out that when we did some follow-up observations of it, it wasn't just a bright flash in the infrared. It turned out to be this radio jet started to form. And over the next 5 years subsequent to that, so about from 2006 to 2011, 2012, this jet changed shape. And then these latest observations that the paper are presenting come from about 2015. And you can see this jet changing shape all throughout that decade or so.
So this isn't a supernova. This is something different.
No, supernovae do not create these big jets like this. So we knew then that this was something different and very new and exciting.
But it also wasn't just your standard, jet emissions from an active galactic nucleus either. It was different. It was new and cool and interesting.
Yeah.
And they've worked backwards to figure out it's got to have been this star being torn apart.
Now here comes the mystery, which is really exciting. If we just sort of set up a theoretical system like this and said, okay, if a star falls into a black hole, what are we going to see? We would expect to see light from the very high energy part of the spectrum first. So we would expect to see X-rays. We would expect to see some visible light as well. We didn't see any of that for this one.
So what's going on?
Well, the way the authors have explained this is by thinking about, well, maybe the orientation of this black hole is such that the disk we're kind of looking along the disk, if you like. So the poles are going perpendicular to our line of sight, and we're trying to peer through the disk to see the black hole, which is a difficult thing. Well, you can see it anyway.
Yeah, there's a lot of stuff in the way.
Yeah. So when this star gets too close and it does this first flash when we'd expect to see the X-rays and the visible light, actually the disk was a bit in the way. And instead of seeing all that visible light, the disk itself absorbed all that high energy light, and it re-emitted all of that light back out in the infrared.
Right, and so it's giving us a signal which we didn't expect to see because of that interaction. If we'd been looking at it from a different angle, we might have seen it. But because of the angle we're looking at it, we're seeing this secondary effect instead.
Yeah, so the disk has put out all that infrared light, which was what was originally spotted back in 2005.
Right. What's the mechanism, just thinking about star getting a bit too close to a black hole, a black hole is just a lump of mass in the same way that the sun is a lump of mass. The Earth goes around the sun. We don't get torn apart. And yet this star is getting torn apart. Why? Why is the star getting torn apart?
Yeah, that's a really good question. We don't know the details for this particular star, but we can propose some scenarios as to how maybe what happened to this poor individual star.
Yes. It's hard not to anthropomorphise these things, isn't it?
Poor thing.
It's just a star. It doesn't feel anything.
No. It either wandered a bit too close, so it might have been in a very highly elliptical orbit, and we do see some of the stars around the centre of our own galaxy doing this. And that orbit got perturbed, whether by another object or whether just by decay.
So you're saying it just got flung too close?
Yeah.
Even so, I mean, is it that as the star gets really close to this incredibly dense, high gravity environment, the fact that being that close, one side of the star is actually even closer than the other side of the star. It's feeling more gravity, and it starts actually getting pulled apart in that way?
Definitely, yeah. Yeah. So what happens is the gravitational force, let's say on the star, a side that's facing the black hole, is so much bigger than the side that's away from the black hole that the black hole itself can just pull off the material. It's much more attracted to the black hole than it is to the star itself. So it just sort of starts to pull off in a big stream, if you like, as the star goes past. Maybe that's happened before, but likely the star just came too close, and then once you started to pull your material off, then you're in a lot of trouble.
All bets are off at that
Yeah.
point. You hear sometimes people talking about what would happen if someone fell into a black hole, and the term spaghettification comes up, which is exactly this, that if you were falling in feet first, then your feet would experience such strong gravity before your head does that you would get strung out like this big long piece of spaghetti. And maybe it's a little bit like that. Not quite, not on the surface, but a bit further away, that the star is being ripped apart because the closer side is a bit too close. So the whole concept of black holes at all, I mean, if we can come back around to this really interesting thought, that we're making all of these observations, we're seeing things there which are influencing anything from nearby stars to the dynamics of entire galaxies, black holes and supermassive black holes. It staggers me that we still don't really know very much about what these things actually are. That they're actually beyond physics as we know it. We've applied Einstein's theory of general relativity. This is where these notions come from. And we've applied it to the point where other physics breaks. We've broken physics. We've made this construct. We think we've found them. And we don't know what they are. And that's awesome.
And our minds start to break as well.
Yeah.
So like when I say a neutron star, for example, I can say it's a big ball of neutrons. And I don't know what you imagine a neutron to look like, but I sort of think of a little white sphere with a big N on it.
See, for me, they're grey. I don't know why they're grey. I'm imagining a little seething grey lump of stuff.
Of course, that's not really accurate, but
No.
you can imagine what a ball of neutrons might be like.
Sure.
If I tell you to imagine what a black hole might look like,
No, I've just got a sphere with a sign on it that says "Go no further." I cannot imagine my way into it. And physicists talk about the singularity at the center of a black hole, and basically what they're talking about there is, look, at the point where gravitational collapse takes over, you run out of mechanisms to stop it. You run out of physically ways to keep that ball up. Once you've gotten past, the neutrons, we can't stop them coming together anymore. And there's maybe some other mechanisms inside there. Maybe we can get down to sort of the quark level. But beyond that, you can just keep coming up with these, well, what if we throw a bit more mass in there? What if we just put a bit more in? And you get to the point where we've got nothing left, in which case it just keeps contracting down to a point, a singularity, which is infinitely dense. And as soon as you start talking about infinite anything, you're in really dodgy territory, and physics is broken at that point. And we just have to stick our hands up and say, we don't know. We're waiting for more information now.
yeah.
And it's fascinating that we can observe what we think of these things without knowing what they are.
Yeah, or even particularly imagining.
Yeah.
Even in our own minds. I would say if you're going to pick up the three big topics that are really going to mess with your mind in astrophysics, then you're going to pick dark energy, which we'll touch on in a future episode, I'm absolutely sure. Dark matter, which we've started to touch on, and I'm sure we'll return to. And of course, black holes.
Yeah. I mean, it's why Stephen Hawking, when he was alive, was such an enigma, is because he spent his time thinking about these sorts of things, whether it was the Big Bang, which is sort of the ultimate singularity, this is the universe coming from a point and coming into being, or the singularities at the center of black holes and what's inside these things. And it's a combination of absolute cutting edge theoretical physics and cosmology and pure guesswork in a way. It's inspiring and scary stuff. It's weird.
Yeah. And so I have a really nice quote here, which I thought would be worth sharing about black holes. It comes from John Archibald Wheeler, who has quite a repertoire.
One of the really big people in gravity. He literally wrote the book Most theoretical physicists have a massive, thick, several inches thick tome called Gravitation on their bookshelves, and it's Wheeler, and it's terrifying. It's just, wow.
Fortunately, the quote is not very terrifying. It's very nice.
He
describes black holes. Space-time tells matter how to move, and matter tells space-time how to curve. Now, we're not going to discuss what space-time is at this point, but I think it's nice to leave it there to think about, actually, we are talking about not just objects floating out there in this vacuous thing that doesn't make any sense. We do have this underlying construct in the universe called space-time, and we're going to explore that, I think, in a future episode, which is very exciting.
Black holes are literally mind-warping things. Well, we're at the end of another edition of Syzygy. This one's been about black holes, and my brain needs to go and sort of expand a little bit. I think I need to go for a bit of a walk around in the sunshine and get my head out of black holes for a minute. Because you do as a physicist and as an astronomer, you get quite used to throwing around these things, and then you suddenly come back up for air and realise, none of this makes any sense. This can't possibly be real. I need to go and have a coffee and just have a lie down for a minute. Anyway, joining me as ever in this edition of Syzygy has been Emily Brunsden. We have recorded this, as we usually do, in her office here at the University of York. If you want to get in touch with us, there's a couple of different ways that you can do it. You can get in touch with us through Twitter, and they can do that how, Emily?
You can send your message to @SyzygyPod. We are looking for questions. They will not go into a black hole. They will come straight to us.
They definitely will. Definitely will. No question about that. Or you can contact us through our website, syzygy.fm. There's a little form on there, and you can get in touch with us and send us your questions, send us your comments. Just say hi. That'd be nice too. The other way you can say hi is by leaving us a review and some stars on your podcast directory of choice. That helps other people find us, helps other people to share in the excitement and the joy that is astronomy, cosmology, physics, and other really nerdy things. But until next time, that's pretty much all we've got for today. So how about we say bye-bye?
Yep, goodbye.
Catch you next time. Title:
Death by black hole.
Death by black hole.
Or black hole consumes star. Astronomers watch and do nothing.
Oh, that's getting very dark.